Welcome back, guys. If you're joining me, you are ready to see part 2 of the gas laws. Okay, so the second law we're going to talk about is Charles's law. And what Charles's law tells us is that the volume, right, the space the gas takes up. Ooh, my pen doesn't want to work. There we go. All right, the volume of a gas is directly proportional to the temperature. And this is assuming that the amount of gas you have stays the same, and we are keeping the pressure the same. And we have to assume that if volume is changing, that we have a flexible container. All right, so my very nerdy hint, King Charles was vicious over the townspeople, is to help you remember this formula. So when we have a proportionate relationship, right, if one goes up, the other goes up. If one goes down, the other goes down. And we can signify that when you write stuff like a ratio. So V1 over T1 is equal to V2 over T2. And V1, of course, is our initial volume. T1 is our initial temperature. V2 is our final volume. And T2 is our final temperature. So, the only other big thing, we have this formula to follow, the only other big thing, temperature must be calculated using kelvins as the unit. Main reason being, kelvins is always positive. And so, particularly when we're dealing with a proportion, as volume can never be negative, our temperature, if we'd had, negative 5 degrees Celsius or something, we'd end up with one of our volumes being negative, and that just doesn't exist. And so kelvins is a scale that's solely positive, and so we see that occurring. All right, so if you're in class, we're going to do a little demo. If you're just watching this, you'll have to ask a friend about it or ask me or your teacher. All right, so when it comes to solving these problems, like I said before, they give you a bunch of information. Underline or highlight everything given to you, and then it's kind of like a puzzle. Figure out how does this all connect and make sense. So, example 2. Oxygen at 40 degrees Celsius has a volume of 2.32 liters. If the temperature increases to 75 degrees Celsius, what will the volume be as long as pressure and the amount of gas is held constant? All right, so we have oxygen at 40 degrees Celsius, so that must be our initial temperature, and it's given us a volume, so we will make that the initial volume. If the temperature increases to 75 degrees Celsius, so that is our T2, what will be the volume as long as pressure and the amount of gas is constant? So what will be the volume? V2 is our unknown. So before we really jump into this, we know that we have a directly proportionate relationship, and so our formula V1 T1 is equal to V2 T2. Before we even start to rearrange and things like that, we need to make sure that our temperature values are in degrees Kelvin, not degrees Celsius. So let's just do that really fast, so later when we go to plug in our numbers, it's easy peasy. So to go from degrees Celsius to Kelvin, we are just going to add 273, right? So 40 plus 273, our initial temperature, and We don't have to think about this. We can just grab our calculator, right? 273 plus 40 gives us 313 Kelvin. And let's take a look at our final temperature. So 75 plus 273. Go ahead and put that in our calculators. Our final temperature is 348 Kelvin. All right, so now let's go ahead and solve. So just like before, you can just plug that into the formula as you see it, so each respective variable, or like I like to do, I like to rearrange variables so I'm only plugging in numbers once. So we are trying to solve for final volume. So getting V2 by itself. Now this is a little different than last time. You're going to need to cross multiply and then divide. So we're going to rearrange the equation, right? So cross multiply. So T1 times V2 equals V1 times T2. And then, to get V2 by itself, we divide by T1. So that's what I mean by cross multiply and divide. And if we divide on one side, we divide on the other. So our final formula, in order to figure out what the final volume is, we multiply initial volume by final temperature divided by initial temperature. And let's go ahead and do that. So we'll just plug these numbers in. So our initial volume is 2.32 liters. Multiply that by our final temperature, which is 348 Kelvin, and divide that by our initial temperature, which is 313 Kelvin. So now we can plug these values into our calculator and solve for our final volume. So 2.32 times 348 divided by 313 is going to give us 2 point. Okay, my stylus doesn't like doing points. Hold on, let me increase the size. Maybe there we go. Nope. There we go. All right. 2.579 blah blah blah. And we need to look at significant figures. So 40 degrees Celsius. Ooh, that is one significant figure. 2.32 is 3, 75.0 is 3, but because of that 40 degrees Celsius, it is one significant figure. So, bad problem writing, Mrs. Hunter. But, so 2.5, if we want one significant figure, needs to be 3. And take a look at those units. I love the units in these problems. Liters times Kelvin, nothing changes, but Kelvin divided by Kelvin is going to cancel, and so you're left with liters, which is a unit that makes sense for measuring volume. So this is another kind of double check that you have successfully navigated one of these problems. So our final answer is 3 liters, and let's see if that makes sense. Temperature increased, and volume went from 2.32 up to 3. So, proportionate, directly related. And that's how you solve a Charles Lobb's problem. Hopefully this makes some sense, right? So if we want to keep the pressure the same and we haven't changed the amount of gas, if we increase the temperature, right, we're going to see those gases moving more. And if we're keeping pressure the same, then volume's going to have to expand. This way, the number of collisions with the size of the walls don't change. So hopefully this makes some sense. A really good example of this, if you've ever woken up on a cold morning and you go to get in your car to drive to school or somewhere, and the check tire pressure comes on. and that's because since that weather is dropped and the volume can't change, we see that the pressure actually goes down. But if we wanted to keep pressure the same, we would actually need to, if the temperature drops, we'd have to change the volume of our tire, which is not very useful. So there you have it. I'm going to end this video here, and if you need some more, check for part 3.